Hello everyone, the topic of our paper is failure service pattern mining for exploratory service competition. These are our authors. I will introduce the paper from these 5 aspects. Firstly, I will introduce the research background. In some situations, end users can't make a thorough experiment plan in advance. They may want to dynamically adjust the composition logic at runtime. To solve this problem, we provide users with exploratory service composition so that users can dynamically adjust the processes according to their individual needs. There are 2 kinds of dynamic adjustment, which are dynamically ending services and dynamically debug the build field processes. After the exploration, users can write the success or failure service processes back to the service library to improve the reusability of these service processes. In the process of gradually building domain services, lots of processes are generated, and there is a regular association between the services. For example, these 2 services appearing in pairs that are heavily used in exploratory service competition. It shows the characteristic of large granularity and high reusability. Related research refers to this service fragment, which frequently appears as a service pattern. Among them, there are success service pattern and failure service pattern. According to our research, there already have so many excellent work about the success service pattern. So according to this introduce, we defined 2 issues. The first one is how to express a stable and reusable service pattern. The second one is how to mine the failure service pattern from the service competition processes that users have explored. To solve these 2 issues, we have conducted related research. The overall service pattern mining can be divided into 2 categories. One is log-based service pattern mining, and the other is process-based service pattern mining. Through understanding of these algorithms, we find they are all aimed at the mining of success service patterns. There is no mining method for failure service patterns. Considering the advantages and disadvantages of each algorithm, we finally decided to extend G-span to implement an algorithm for mining failure service patterns. According to the background, the research content has the following 3 parts. The first one is the model definition. The second one is the failure service pattern mining algorithm. And the third one is the prototype implementation. First, we model the exploratory service composition process instance. Each exploratory service composition process instance contains a track set, which contains several failure tracks and 1 success track. There is a derivative relationship between these tracks. For example, S1 in track 1 is the successfully executed part after dynamically ending S2, S3, and S4 executed it and found that the execution result is incorrect or the intermediate data is not satisfactory. So, S2 is used as the probe point and derive track 2. in which in the track 2, the successful S1 part is cloned directly. S2, S3, and S4 are cloned and initialized to add new activities until a correct execution track is derived, as we can see in this figure. And we model the service pattern as a four tuple, including the service pattern ID, the activities and the transition relationships in the service pattern, and the type of success or failure. After the modeling, the following is the main part of our algorithm. First, a set of failure tracks are abstracted as a graph set we called D. The vertices in front of the probe point on the track are marked as the success point, and the vertices after the probe point are marked as the failure point. Then we sort the vertices and edges in D based on their frequencies, and remove the infrequent vertices and edges. Then sort the remaining frequent edges in DFS lexicographic order. In order to mine the failure service pattern, the subgraph mining is performed only for 3 kinds of frequent edges, such as in this figure. These frequent edges must contain at least one probe point or failure point. Extend each frequent edge that meets the condition to obtain the DFS coding tree. Convert the DFS coding tree whose support degree is greater than the minimum support degree into frequent subgraphs. Repeat this process until all frequent subgraphs are obtained. Finally, the obtaining frequent subgraphs will be filtered to get the failure service patterns. And this is an example of our algorithm. The third section of the research content is the prototype implementation of the algorithm. Exploratory service composition environment is an online service composition system developed to support the FSPMA algorithm. This is its architecture. The modules of exploratory service orchestration tool, runtime user interaction, execution engine, and service library are the fundamental modules of the environment. For this mining part, the module of service pattern mining has 2 data sources, which are the service composition process instance generated by running runtime user interaction, and the historical service composition process instance, which saved in the service library. Because the tracks of the process instances can be divided into 2 kinds, success and failure, this module has two submodules. One of them integrates the FSPMA algorithm to mine failure service patterns from failure tracks. The other integrates the GSpan algorithm to mine success service patterns from success tracks. These service patterns are written back to the service library in the end. Therefore, the function of service pattern management is developed for the module of the service library to manage the service patterns. And the following describes the experiment and analysis of our algorithm. The dataset concludes 1,405 processes crawled from the My Experiment research community, and 10,490 failure process tracks are constructed through process simulation based on the crawled data. The FSPMA algorithm in this study is compared with the G-span and TKG algorithm. When the mining accuracy in this research is the same, we observed the impacts of different mean sub, the number of tracks, and the number of mining results on the running time of the algorithm. First, when the number of tracks is fixed at 10,000, we observe the impact of mean sub on runtime. Since TKG is used to find the best mean sub, only the FSPMA algorithm and the G-span algorithm are compared. It can be found that when mean sub is set to 10, the FSPMA algorithm has the highest efficiency improvement compared to the G-span algorithm. Then we set the mean sub to 10 and increase the number of tracks from 1,000 to 10,000. It can be found that the runtime of FSPMA is lower than that of G-span and TKG. In addition, the number of mining results may also affect the runtime of FSPMA. When mean sub is set to 10, it can be seen that as the number of mining results increases, the runtime of the FSPMA algorithm is significantly lower than that of the G-span algorithm and the TKG algorithm. So, in summary, the FSPMA algorithm can effectively focus mining on the generation of failure service patterns, avoiding the mining of the entire tracks of service competition process instance. The efficiency is improved under different mean sub and the number of tracks. And when the mean sub is set to 10 under the current dataset, the efficiency of FSPMA is improved the most. And under mean sub is set to 10 as the number of tracks increases, the efficiency improvement of the FSPMA algorithm is stable at about 43% compared with the G-span algorithm and about 50% compared with the TKG algorithm. At this session, we introduced the application of the failure service patterns which we mined. We used them to improve the accuracy of service recommendations. In the traditional service recommendation, we consider the semantic matching and the analysis of process instances. Their values are called mu and lambda. According to these two values, we can get the strings of dependency which is used to recommend. However, this recommendation method also recommends the service where their strings of dependency are high, but there are a large number of error process instances during the analysis of process instance. Therefore, we improve the traditional service recommendation method by using the failure service patterns. which can improve the accuracy of service patterns. Which can improve the accuracy of service recommendation. For example, in this bioinformatics process, the traditional method does not consider the failure service patterns. In these cases, these 3 services are recommended. After consider the failure service patterns, the fragment H to R, which is used to recommend by the traditional method, is a subsegment of the failure service patterns. Although its reuse is high, the wrong process instances are mainly used in the analysis of process instances. This recommendation may cause the execution of the current process to fail. After considering the failure service patterns, this problem can be effectively solved, and the recommended results are like this. Now let's have a summary of our paper. This paper focuses on the issues related to mining failure service patterns from failure tracks of exploratory service competition instances. An exploratory service competition instance model and a service pattern model are defined at first. And then we propose the FSPMA algorithm. Besides, the prototype is introduced to support our algorithm. To prove the efficiency of our method, the evaluation experiments are given to compare the FSPMA algorithm with the G-span algorithm and the TKG algorithm. Finally, we use the failure service patterns to improve the accuracy of service recommendations. In future research, the incremental mining method will be studied to support the dynamic evolution and timely update of the service patterns in the service library, and the evolutionary trend of service patterns will be analyzed. In addition, the experimental verification of the failure service pattern applied to service recommendations will be realized. This is all the content of our research. Thank you for listening.